Hello, my name is Burak Kantarci. I'm an associate professor at the University of Ottawa and the founding director of the Next Generation Communications and Computing Networks Research Lab at the University of Ottawa, and also the founding director of the Smart Connected Vehicles Innovation Lab at the University of Ottawa's Canada North campus. I'll be presenting our work titled Bridging Connected Vehicles with Artificial Intelligence for Smart First Responder Services. And this work was also published in IEEE Global Conference on Signal and Information Processing Conference, GlobalSIP, in November 2019. So let's get started. This is actually an application of smart transportation. So when we say smart transportation, we mainly talk about three pillars. One of them is sensing, which primarily uses data from camera, radar, or LiDAR sensors. And the other pillar is processing. Of course, we need graphical processing units or tensor processing units. And of course, we need to be integrated with an efficient communication infrastructure, or just like integrating the connected vehicles with the 5G network. When we integrate connected vehicles with smart city services, what do we expect? Well, we expect to receive safety applications or non-safety applications and services from connected vehicles. And these vehicles also provide tremendous amount of data as they are a part of this, they become a part of this ecosystem. And since they are equipped with computing and storage resources, they can also serve as edge resources, edge nodes in a network that can provide computing or storage as a service. And of course, they can be individual users in the network receiving services from other vehicles in this network. And there are several other opportunities and use cases that will become available as the connected vehicles get integrated with the smart city services. The problems with our today's transportation system is mainly the accidents. And you see the statistics in this slide. So nearly 1.3 million deaths on the roads worldwide, and an annual fatalities only in the US alone is 40K. That's what the World Health Organization reports. And the accidents cost also the 3% of the country's gross domestic product. Now, what we want to come up in a scenario like this is, okay, we have this task of driving, which is hard, difficult, and tiring for the users, but we take advantage of the data that is provided by the vehicles from the driving events, and we have them undergo effective processing so that we can make artificial intelligence backed decision support systems for the connected vehicles on the roads. The problems that we are facing in transportation is, as you can see here, mainly human error, or the road structure being unsafe, or the vehicle being unsafe, maybe a malfunctioning sensor, or this is actually what we're focusing in this work, inadequate post-crash care. So it is misjudgment of the post-crash scenarios. Now, what are the solutions against these problems? Well, autonomous driving, of course, that is one solution, but we know that and level 5 L5 type of autonomous driving is not going to happen very soon. It will eventually, but not very soon. There's also license plate recognition to be able to track the vehicles, and monitoring the driver behavior is one solution. Suggesting alternative paths and also recognizing road signs. These are the solutions that are being proposed against these problems in transportation. But we don't have many solutions against the post-crash misjudgments. What do I mean by that? Think about a scenario like this. So we have an accident here, okay? And we don't know which first responder or which set of first responders are going to be responding to this event. So is it going to be only the police, or do we need an ambulance, or do we need the police, ambulance, and the fire truck, all of the first responders, to be ready there? Well, our solution, proposed solution here is, okay, capture this event by the camera footage, dash cam footage, okay, and have that image be processed by our detection model here, AI-based detection model here, which I will be talking in a few seconds. And the output of that decision will tell us which set of first responders are needed to respond to this scenario. Because currently what we're doing is we need all the first responders to be there, because we don't know whether we're going to be needing an ambulance. We don't know whether a fire truck is going to be needed. We need all of them, all of the first responders to be there. But maybe we only need just the police there to report the accident. Okay, what do we want to achieve here? We want to have faster call for emergency help if there is an emergency situation. And we need more precise information here about the accidents. And of course, we want to lower the administrative costs and the labor costs in this type of services. Okay, now our methodology is, as you can see here, we gather data from publicly available videos on the internet, and we captured 268 road traffic images of different types of events. So this was a very laborious task. So we split this data set into training and validation and test sets. So the partitioning was 75% by 25%. And we hand labeled these images. Okay, so one category of scenario doesn't have any accident. And we have low severity accidents where we only need the police to respond. There are medium severity accidents where we need an ambulance to be present there. And there are high severity accidents where we need a fire truck to be there. Okay, of course, lack of data and computational resources are always the roadblocks in this type of research. And one of the useful instruments here is image augmentation. And the techniques that have been found effective are, as you can see here, a 5-degree rotation, a slight image warping, and horizontal flip, and noise manipulation. And another good instrument here is using the pre-trained models and also applying further effective training methods on these convolutional neural networks, and of course introducing further hyperparameter tuning techniques on top of them to see whether we can get a better performance. And we have actually tried these convolutional neural network backbones, as you can see here, like VGG 16, 19, ResNet 34, 50, and so on. And hyperparameter tuning is another useful instrument here we have applied to the ResNet backbone. So for the optimizer, we went with the adaptive moment estimation optimizer, and the loss function that we're using is the categorical cross entropy loss. And for the learning rate, we use different approaches here. So a static learning rate has been applied to all of these backbones, and then we went with the best one actually for further experiments. But we also applied cyclical learning and also a slight cyclical learning as well. So when I say slice, we partition the model, or slice the model actually into 4 sections and apply cyclical learning on each section. But with a different maximum bound for the learning rate. So another instrument that we found useful here is unfreezing, which is actually training the last layer of ResNet backbone and unlocking the other inner layers for further training on the new data set. And I'll be showing you the benefit of unfreezing when we talk about the results. So this is the overview of the process. So whenever an accident happens, we get the car camera footage. And of course, this image needs to be labeled here. And the image gets generated and captured by the dashcam footage. And then this undergoes the model that we built. And of course, we have the pre-trained models here, but we of course have the instruments that we used to make the training more efficient and more reliable, alongside the hyperparameter tuning. And at the end, we get the accident detection decision. Not the accident detection, actually, it's the detection for the first responder services, again, in the case of an accident. Now, let's see the results. Okay, these are the results under the pre-trained convolutional neural network backbones. And as you can see here, ResNet 50 gives us the best results. But in terms of computing time, we chose to go with ResNet 34 in the further experiments. So I just wanted to let you know about that. And here, as you can see, these are under a static learning rate, which is, as you can see here, 10 to the power of -4. If you apply cyclical learning approach or slice cyclical, well, that leads to an improvement on the ResNet backbone, as you can see here. Okay, so we went with cyclical learning rate here, as you can see, on ResNet 34 backbone. Now, here's our training performance and our overall accuracy. So when we went with the static learning rate, okay, this was our performance. All right, so we applied cyclical learning on top of this. Around 2% improvement have been achieved. Well, if we apply the unfreezing, which is training the last layer of the ResNet backbone and unfreezing an inner layer for further training, so this is actually almost 3% improvement on top of what we had in static learning under static learning rate. Well, if we apply image augmentation with the effective techniques that I have presented, well, another 1% improvement can be achieved. If we combine the cyclical learning rate, image augmentation, and unfreezing together, well, we can achieve an 88.9% accuracy in our decisions. Now, I'll show you some results here. This is our output heat map and our confidence levels for our decisions. And as you can see here in this scenario, we don't have any accident, right? And this is what we came up with. Okay, so there's no accident. And in this scenario, okay, there's no need for an ambulance. Okay, there is an accident, but we need a police there. No casualties, nothing. But here there might be casualties because of the type of the accident. So we actually need here police and the ambulance. Well, the car is flipped here, and as you can see, we need police, ambulance, and firefighters to be present there. Now, let me present you our confusion matrix. as you can see here, when police is needed, well, we are able to say that, okay, we need a police there. But of course, when we say we need a police there, we also need a fire truck in the actual scenario. And when there's no accidents, okay, out of those 18 cases, we are able to catch 16 of them. And when we suggest an ambulance is needed, actually there's no accident in 2 of those accident situations. And when a fire truck was needed, we actually suggested in 16 of those cases that a fire truck was needed, but in fact we had 19 of those cases. When an ambulance was needed, okay, we were able to catch 14 of those cases, 14 out of 15, and we also suggested a fire truck in only 1 of those cases. So this is actually pretty successful. We were able to achieve almost 89% accuracy in our decisions, but of course we need to improve that, and we have these future plans for improvements. One of them is increasing the focus on vehicles, and to do so we are working on image segmentation models, and of course we are aiming to analyze the movement patterns of the vehicles, so which will require implementing recurrent neural networks in this framework. So this is pretty much it. I hope you enjoyed it. Let us know if you have any questions. Thank you very much.